Welcome, everybody. It's my pleasure to introduce Sayan Mukherjee from Duke University, and today he'll be telling us about a fiber bundle theory for learning shapes. Thanks, Sayan. Take it away.
So, yeah, thanks Henry and Sarah for here and um guess I did this a while ago, so I don't remember what I talked about then, but uh, I'm talking about a fiber bundle theory for shapes today. So I think one of the things that I think about a lot, and I think people who are thinking about applied topology and geometry for the matter are thinking more and more about is really understanding variation in shape. And this is a little one of the points I'm making with this picture is one of the geniuses of Darwin was he started moving away from the lineal perspective of having Platonic ideals for organisms. And he was really stressing much more what we really want to understand is understanding variation in these organisms. And here is a classic example. These are beaks from Darwin's finches. Again, another person early on thinking a lot about this was Darcy Thompson and his classic text on growth and form. One of the data sets I'm going to talk about today is work with something one of my colleagues here at Duke, Doug Boyer, collected, and this is a collection of heel bones across various extinct and extant species. Now, I'm going to be talking about shape today, but some of these ideas are also more general, and I'll touch on that. One of the things you might want to do is take all of these heel bones, figure out some form of similarity or distance between each of these bones. Then you make a little matrix here, and from this matrix you can construct a phylogenetic tree. And the idea here is these phylogenetic trees are encoding something about similarity in the trait, and you can compare, for example, what you get from this shape tree to what you would get from a gene tree. And that could be possibly interesting because if there are deviations from that, you can say, well, maybe this is something that's being selected for. A working picture that we have had in our head is thinking about evolutionary processes as like broccoli or cauliflower. And so things that are very close to each other, they're probably smooth and nicely diffeomorphic. They have, kind of some continuity property. But if I go down the evolutionary tree and then come back up, it could well be that I get things that are no longer diffeomorphic, and you can have a lot of changes. So we'll come back to this picture. So classically, there have been three ways of thinking about shapes. So the old classic way is what are called shape spaces, and this was pioneered by Kendall, and I'll get into that. A more modern version of this is this Lie group or diffeomorphism approach, and this is really came out of ideas from Ulf Grenander. And the third approach, we'll actually talk about approach 2 later on in this talk as well. The third approach is an idea using integral geometry, and these involve Euler characteristics, these involve integral geometry, and that's one of the first approaches and representations that we're going to talk about later today. Sorry, wrong direction. Now, one thing that's interesting, and I'm not going to talk about this so much today, is that all three of these approaches can actually be unified using ideas based on fiber bundles and sheaves. So this is the data itself. This is a tooth. And if you look at it, what it really is it's a mesh. It's a simplicial complex. So the raw data itself, if it's stored as an off file, you get a bunch of 3D coordinates, which is what we see here. And then we see how, 1, 2, 3 go together. 3, 4, 5 go together, so on and so forth, right? So this is actually how the data is stored. So it's really natural to think about these in terms of simplicial complexes and simplices. So simplicial complex, you just glue the the faces of the simplex together. You glue them together such all faces, the simplex are in the complex, and they intersect along common faces. So these are not simplicial complexes. So a less abstract version of what we mean by a shape in this talk is a finite geometric simplicial complex. So you have an embedding, and then you have a geometric simplicial complex, and that's going to be one version. Another version, more abstract version that we sometimes talk about, is this notion of an O-minimal structure. and this came from logic and other set theoretic constructions. And the idea is this is a way of getting some notion of tameness, right? So what you were saying is that you have subsets of RD that are closed under intersection and complements, and you have this property, the first property, which if A is in OD, then A cross R and R cross A are both in OD minus the plus one, so you can add something on. And then property two is you have axis aligned projections are well defined. So you can really think of this as a measurability idea, and we'll get back to that. So given this O minimal idea, there are two kind of important objects that we're going to look at. One are constructible sets. These are collections of compact definable subsets of RD. These are elements of O. And the other is a constructible function, which is a function on a tame set, and it's basically going to have the property that it changes its integer values. So you can start seeing as to where we're trying to get towards an Euler calculus or an Euler characteristics. Okay. So the picture that we have in a lot of this talk is that I'm interested in shapes. Let's say I'm interested in teeth, or it could be heel bones or something like that. And so I'm going to think of my data as living on this manifold, okay? And I'm going to have fibers sitting above the points on the manifold, okay? And there's a projection map. And so, like I said before, the data that lies on a fiber bundle. So you can think about this manifold as my evolutionary process, and these are different kinds of monkeys, right? That are evolving somehow. And then the data itself are going to be fibers. And the way you can think about them, for example, are molars of these monkeys, right? So, and you can think about representing them, for example, as the entire shape. And we'll come back to that, and this is this idea of continuous processes. And what you're going to think is there's some notion of parallel transport, or I have pairwise maps between all of these. Okay. Now, first, one thing we're going to want to do is, can we model shapes without requiring landmarks or diffeomorphisms? And the answer is we can, but we'll talk about how we do that. And the idea is we're going to transform the data or the object into a representation that can be modeled using standard methods. We want this transformation to be injective. The transform space should be nice, maybe a matrix, maybe something usable. And we're going to talk about this towards the end of this first section, which is I want to be able to pull back from the transform space back into my original space, and you'll see why. That involves some analyses and interpretation. Okay. So one of the points that people have made, and you can look at this is from work that Ezra Miller here at Duke has done. There's a geneticist, David Houle, who studied all kinds of the wings of fruit flies. And some of these were mutants, and some of these are normals. The ones up here are all normal. But some of the mutants, they have topologically abnormal veins. And what I mean by that is the fly wing structure is actually qualitatively different. They're losing lobes or adding veins or losing veins, right? So you have something that's qualitatively different. So the question is, if I wanted to use a diffeomorphism-based approach here, I would have problems. Okay, so we're going to look at two topological summaries. They're related. One is Euler characteristics, and the other one's persistent homology. I feel a little bit bad because I actually did not define persistent homology. Is there anyone out there who doesn't know what it is? If you don't, you can give me like 2 minutes, and I'll stop sharing my screen and add some slides.
I think you're fine, Cheyenne.
Okay.
We can feel free to send me an interview or an email if you want to get caught up later. But I think our
okay. Yeah. Sounds good. So why might one want to use summaries? Well, modeling the data, it may be hard. So I'm working with a student of mine on the project of how do I put probability distributions over these shapes, right? And it turns out that's really, really hard, right? Especially if these things are complicated and they can be quite weird, right? So inference, again, on the data might not be robust. Yeah? Oh, okay. And we might not be interested in, for example, capturing the exact geometry. And so we'll go on with this. So our first summary is just the Euler characteristic, which in this case is vertices minus edges plus faces. And what we have is the other thing we have a height function. So let's say this is actually a heel bone that I'm showing you. This is a plane. You take the perpendicular from the plane and start running it through the heel bone and seeing how the Euler characteristic changes. And I can do that for many directions. So this is a mouse embryo heart, and I've looked in this direction, and I've gone distance A, and what I'm showing you is the sub-level set. Okay? Great. And so what I can do, for example, is I can take a hand, and I can start sweeping through left to right, and this is how the Euler characteristic is changing in the hand as I sweep through. And the curve on the far right is what we call the smooth Euler characteristic curve, which just simply means I integrate this and I zero mean it. And you'll see where this, you'll see where I use this, and you'll see where we use this. And so again, we're just counting critical points. Okay. So there's something called the Euler characteristic transform. And so if you take a fixed shape, consider it as a constructible set, the Euler characteristic transform is a map from the sphere to the space of Euler curves. Right? So what we're just saying, object mesh M, direction V, distance T. So I take M, I intersect it with all of the points such that x dot V is less than T, so that's a half space, and I compute the Euler characteristic. And I do this from all directions. The smooth Euler characteristic transform is something very similar, except for, there's a typo here. There should be, life will go on. This should be sect M. Anyways, but the point is, it's again the map from a sphere, but now to functions that are in L2. Okay, and we'll see why we might want to do that. And lastly, there's something called the persistent homology transform, which is basically you're just doing a Morse filtration in each direction V, and you compute 0th, first, then whatever your dimension d minus 1 homology is, right? So it's a map from the sphere to diagrams. Now, one can show, and this was shown in two papers. One was with me and Justin Curry, myself, and Kate Turner, and another one was Rob Greist and some of his students, that there is a relation between the persistent homology transform and the Euler characteristic transform. You have this kind of commutative diagram, and the persistent homology transform has extra information over the Euler characteristic transform. And what I'll do is, as I get further along and start talking about some of the applications, I'll state why we're using one of the transforms or another, and when I get there. So something that you can naturally do is if I give you two shapes, I can measure distances between them by either using the Euler characteristic transform or the smooth Euler characteristic transform or the persistent homology transform. And if you notice, there's an integral here over the entire sphere, right? And we'll come back and we'll talk about, how your computer does an integral over a sphere, because your computer does not. Okay, so one thing that you might have observed so far is this type of Euler integration is really related to things like the radon transform and these kind of, again, Euler calculus. Now, we know in general that inversion of the radon transform is an ill-posed problem. So probably, or at least the most abstract version that I know of an inversion theorem or formula for the radon transform is this work by Shapira in 1991. And if you look at this work, and if you look at kind of the formulas that he's having, this is very, very much a fiber bundle construction. And again, here he's really relying on these being constructible functions and these idea of constructible sets. So this O-minimal idea that I introduced early on is really being brought to bear here. And again, this is to have some minimum notion of tameness, right? So you can do the inversion. Now, one can show that the Euler characteristic transform and the persistent homology transform are both injective maps. Now, this was first shown in a paper with, it was Kate, myself, and my colleague Doug Boyer, And we didn't use Shapira's results there, and we had something that was very almost algorithmic. It was almost like a pseudo algorithm or pseudocode. And our proof worked for dimension 2 and 3. We didn't really try. Well, we didn't get it working cleanly for above dimensions. So later on, Justin, myself, and Kate, and Rob, Rachel, and Mai worked out these results again using Shapira's inversion formula to show that there's some notion of injectivity. Now that's all well and good that it's injective, but those results tell you it's injective if you look at every single direction. Okay, and the question is, how many directions should you really look at? So, in a paper with Kate Turner that I forgot came out maybe 2015 or something like that, when we were doing simulations and on the real data, we should, for 2D data we used 162 directions, and for 3D we used over 700. But one can actually ask a theoretical question: how many directions should you really have? Okay, and this is related to this beautiful paper by Arnold, where he said that if I tell you, right, where the critical points are of a function, can you tell me how many homologically different functions there are that have these critical points? And what's amazing is he gives a closed form solution for it, which is pretty cool. Okay, so now I'll give you a result.
That paper by Arnold, is that only for functions on the real line?
Yes. Extending this to 2D is going to be brutal. Yeah. Because of orderings, right? And that's where the Bernoulli, Euler, Springer, and the numbers and the Coxeter group comes in. The Coxeter group comes in because these are kind of controls on permutation, right? So extending those to from the real line to anything where you don't have a clean notion of ordering is going to be really, really hard.
Okay, thanks.
Okay, so now I'm going to try to give you some idea of how we can control how many directions you need. And this is kind of the frame, the story that we're going to tell. We're going to define a moduli space of shapes, okay? And all of these shapes are going to be embedded simplicial complexes in RD. Just think about in R3, right? Like I was showing you earlier in terms of the teeth or the heel bones. Okay? They're going to have two parameters. One is delta, one is k delta. So the first parameter is at every vertex, there's a lower bound on curvature. And I'll make this a little bit more precise in the next slide. But the intuition is at any vertex, I have some lower bound of curvature. And the argument is if things are really flat, it's hard to tell apart something that's really flat from something else that's really, really flat. The flip side of it is I actually may not care because I might just say it's flat. Okay? So the other thing is I need a control, we call it k delta, which is an upper bound on the number of critical points as I sweep in any direction. Okay? Now, it's a little bit more than that because what we're saying is that if I look at any direction, let's call that direction W, okay? Not only do I need an upper bound of k in that direction, if I look at any ball of size delta around that direction, right, I need an upper bound of k for any of the balls around there, okay? So again, this is some notion of continuity of what's going on. And shoot, well, I didn't. I'll add a picture in a second. Let me. I guess I'll have to do it real time. Okay, but that's okay. Okay, so I told you there's a notion of curvature. This is a notion of curvature. I have a geometric simplicial complex. K be a vertex of K. We set the vertex X is delta observable if there exist these balls such that the Euler characteristic HV changes at V of X for all of these, any of the vertices in this ball, okay? So you're saying that if I take a small cone, right, within that cone, I'm going to see, in a way, the Euler characteristic is going to change more or less at the same points around that cone, okay? And let me say a few things. Sorry about this slide. So another point is, I think Kate's going to be talking in a few, maybe a month or so, and I'm not exactly sure what she's going to talk about, but she actually may talk about some very related things. Okay? So, sorry. Okay. I'm trying to draw a sphere. So I drew a sphere, okay? So what the next results you're going to see about, but what I'm really talking about is that the Euler, these results is you have a stratification of the sphere, right? So what I'm going to say is if I take a sphere, I can cut it up into, let me just add lines. Right. So what I can do, sorry about this, is I can start cutting up the sphere, right, in terms of these kind of separating hyperplanes. And what you can show is that I'm not good at doing this real time. Okay. So let's say that this is the sphere and this is one of the cuts. So what I'm telling you is any cone, right, that hits in this region has a linear relation in a way between the Euler characteristic curves. So the Euler characteristic curve, if I go in this direction, I can recover what the Euler characteristic curve could look like in this direction, right? And the number of partitions that I need to make depend again on that lower bound on that observable angle and the curvature. Okay, so given that, you can give this upper bound on how many directions you need to tell apart any two shapes in this moduli space. So this moduli space is basically, it's an infinite number of shapes, and probably you can think of them continuous, right? But at the end of the day, you can actually get an upper bound on how many shapes, how many directions you need to tell apart any two shapes. Now, what I'm showing you right now is a theoretical result. There is a related and interesting applied question here. And the applied question is the following. The way that micro CT scans, so the way that my colleague Doug or many other people got these bones imaged is via micro CT. The way micro CT works is you X-ray your object from many, many, many directions, and then you basically reconstruct the mesh from those X-rays using the inverse radon transform. Okay? Now, one thing that's quite relevant is for many diseases, or as we try to observe people, in more detailed way, you don't want to radiate the hell out of people regularly, right? So one very basic question is, if I gave you a radiation budget, can you tell me how many directions and which directions I would need, right, to be able to get an epsilon reconstruction of the shape, right? So this is also a real problem, okay? Great. Now, there's a reason why we also looked at the smooth Euler characteristic curve. And that is, if I looked at the smooth Euler characteristic curves, right, what do I have? If I look at L different directions, I have L curves. If I have L curves, I can define an inner product, right, because these things are in L2. And there's a classic notion in statistics, something called an exponential family model, where if I can take if my objects admit an L2 norm, right, I can think about some parameters theta, and I can define probability distributions this way. And what's nice about this, I'll give you two examples, is if I took that smooth Euler characteristic curve and I discretized it not also in terms of the points on the curve, my shape has been turned into a matrix. It's an L by T matrix. And we actually know how to put distributions. We have many ways of putting distributions on matrices. One classic distribution is what's called the matrix variate normal. It has three parameters. It has a mean parameter, which is what your mean matrix is going to be. It's got a mu parameter, which models the covariance between the curves, and a v parameter, which models the covariance between points in the curve. So now what I can do is I can take a shape, I can turn it into a matrix, and I can define likelihood models, and I can start doing more formal statistics with this, and we'll talk about this. Now, if you did not want to discretize it with respect to the points, with respect to the curves, discretize the curves, there's a model, which I will get back to very soon, called a Gaussian process model, which basically lets you model these curves, okay? And we'll jump into that very soon. I guess I just said that. These are heel bones from two different angles, and this is a result on real data. There are heel bones from 106 primates. We compute pairwise distances between them using the persistent homology transform, and then we did multidimensional scaling to project it back down to 2 dimensions. Okay. These are what are called great apes. The gibbon is a lesser ape. This is a spider monkey, a baboon, a macaque. This is an extinct old world monkey. Many of these are old world monkeys. Spider monkey's not, it's a new world monkey. Howlers, monkeys, squirrel monkeys, and this is an extinct new world monkey. These are all new world monkeys, and these are all lemurs, right? So it falls into something that's interesting in terms of what we would think in terms of evolutionary. And you can make prettier picture, which is what my colleague Doug did, and relate it to the taxa. And oh yeah, the reason why we use the persistent homology transform is when you're looking at distances between these shapes, the persistent homology transform is a good bet because more so than the smooth Euler characteristic transform or the Euler characteristic transform, it has nice Lipschitz properties, right? So it has better smoothness properties. Okay. So if you compare 3 methods, this is using persistent homology transform. This is using a diffeomorphism-based automated continuous landmarks. And this right here is using classical Kendall statistics. Now, visually this looks better. There are arguments as to why this may be better, but going back to the broccoli picture, if all of my objects lived really, really nearby each other, this method would do the best. The diffeomorphism method would actually do the best because it can give you the best resolution. But this method has problems when things are no longer quite diffeomorphic. And so things that are far apart can start really warping or shearing the space, right? And so that's the issue that you sometimes get here. And there's a really, really interesting question, right? That has been studied by some people, but we don't have more extensive understanding of what is a good gold standard distance for shapes that are not diffeomorphic, right? There's some work done on, in terms of things like Hadwiger ideas, right? But, how general that can be made is not really clear. And then other people, you might argue, well, what about something like a Gromov-Hausdorff distance? But, can't really compute it, number one. But number two is it could be really brittle. So it's still, what's still open is like what would be a really good gold standard notion of distance. So I'll tell you some more, and what I'll tell you a little bit more is how can I use a shape in a regression model, in a statistical model, okay? And the context for this is an application in oncology or something called radiomics. So this is a person's skull. This is an MRI, and this right here is a glioblastoma, which is a brain tumor. Okay, and if we were to segment it, this is what it looks like. And we're going to ask this question: if I give you 92 patients, and I have their gene expression data and the MRI data, okay, TCH is the Cancer Genome Atlas. So I told you I have biomarker data from 9,215 genes. I have morphometric features. These are features that radiologists and oncologists have agreed to use or think are good features to use. These I don't even care about. They're like 5 numbers about how big, wide, whatever these are. These are 7,200 features that you can generate using the smooth Euler characteristic transform. And I'll tell you why in a little bit we're using the smooth Euler characteristic transform. And what we want to do is either predict disease-free survival or overall survival of the patients. Okay? That's our goal. So the first question is, which of the following best explains variation in the clinical trait? The gene expression, the morphometric features from the radiologist, or the topological features? So we're going to use shapes and regression models. Now, I'm going to tell you about a Gaussian process, but before I tell you that, there's a field of statistics called functional data analysis. And what people in functional data analysis work on is they say, well, what happens in my data is a curve, is just one-dimensional curve. Sometimes two-dimensional, but typically one-dimensional curve, right? How do I model it? How do I use it to, do regression or predict something, okay? And that field is pretty well developed. And almost always, not completely true, there are exceptions. People typically think about curves that are smooth curves in L2. Now, one of the nice things about the smooth Euler characteristic transform is once you've mapped the shape into the smooth Euler characteristic transform, you are back into the domain of functional data analysis. So you can start using a lot of the classical statistical tools that exist in functional data analysis. Okay? Okay. So one of the objects is something called Gaussian process regression, and you're going to see Gaussian processes again later in this talk, but this is kind of the most straightforward version of it, okay? I have a stochastic process over some domain, okay? And what I know is there's a mean function mu and a covariance kernel, okay? And I have something is a Gaussian process if for any finite realization of this infinite dimensional stochastic process, right, the function x1 through xn is modeled by a multivariate normal, okay? And what's the mean of this normal vector? It's just the mean function at x1 up through xn. And what's a covariance? It's a kernel function. And I'll specify a kernel function, right? So what's nice is, let's say I'm given data x and y. X are my smooth Euler characteristic transform data. Y are, let's say, disease-free survival, so a real number, okay? Okay, and then now I give you some new points x star, and I want you to predict how long the patient, survives on these new points x star, right? So I'm trying to get an estimate of f star. Well, what's really nice about Gaussian process regression is f star is normal, right? And depending on, let's say x star were two new points, then f star would be, bivariate normal. If you're looking at 3 new points, it'll be, three-dimensional normal. And not only that, we can actually give you what these means and these variances are, right? And they have a nice closed form expression. Straight linear algebra, you do have to do order n cubed inversions, inverted order n cubed matrix, but there are also tricks around that, okay? And what's also nice is you get an estimate of uncertainty on these efforts. Okay. So this is sometimes also called a kernel model, and this very, very much falls under standard functional data analysis. And so if you hear about things like Gaussian process models or spline models, right, these are what we're talking about. So this is what it really in a way looks like. At each data point, I have a little bump, and it's weighted, and it's a linear combination of these. Okay. So one can use a linear kernel, right, which is just a correlation between the two different smooth Euler characteristic curves. You can also take some Frobenius distance to compute the distance between two of these smooth Euler characteristic curves. And then we looked at two different kernels. One is the Gaussian kernel, or sometimes called a radial basis function kernel, and another one is something called a Cauchy kernel, which has a little bit fatter of a tail. So if people have learned or thought about unsupervised dimension reduction and algorithms like t-SNE uses ideas like the Cauchy kernel. Okay. These are the results. We get the best results with the Cauchy kernel, and kind of the thing that we're trying to highlight is the smooth Euler characteristic transform is actually doing better than the other variables. And this just means how many times the topological feature did the best in all of our runs. And we're doing basically, I think we leave out 10% of the samples in each run, and then estimate how well we do on that 10% left out. We do that again and again and again. Now, one of the things that's interesting is, one question is, why do we do better than gene expression? The reason we do better than gene expression is very, very unstable and noisy. Okay. The other question that would be really nice to explore is why do we think topological features actually say something about disease-free survival, right? And one version of this is we know that tumors that are more malignant have more fingers, and they are like digging more into more invasive into the tissues around them, right? There's certain things that surgeons know, that if you have a breast cancer and it's like dead in the middle or necrotic in the middle, right? Outcome tends to be better, right? So that's a statement about Betty 2, right? We know that if the tumor is splintered severely, chances of it being malignant go way up, right? So that's a statement about Betty 0. So there are some relations, and making this more formal and relating it more to the physiology and the molecular biology is interesting. Okay, so there's a second question, and the second question is, can you tell me what parts of the shapes are most different between, let's say, two classes? So we could go back in the tumor saying people who lived long versus didn't live long, right? What subparts of the glioblastomas are the most different, right? And we're going to explore this in molars because we understand molars. I should say, I have colleagues who understand the morphology of molars much better than we would understand what would happen in a brain tumor. Okay, so this is a notion of the variable selection problem, and it's again a regression framework. And these are five different monkeys, anyways. So this is we have a paper on bioRxiv. We call our method Sinatra because it's smooth. I'm joking, kind of. And so let's say this is species 1, and let's say species 2. I call this class 1, class 2. So what I do is I run through the shape, right, and I get this. Now I'm looking back at the Euler characteristic transform, and I'll tell you why in a second, okay? So this is just filtering in one direction. And then what we do is we look at, for let's say, shape class 1 versus class 2, right? We look at where do they look the most different? In what directions and at what point do they look the most different, okay? So those are colored in red. And then what we do is we take those red points, or red variables that we've marked, and we pull that back onto the shape. And we can do that because the Euler characteristic transform has an inversion in a way, okay? And then we visualize that. And the way we visualize that is we have an enrichment statistic, and this enrichment statistic somehow tells us which of these, how much evidence there is of a difference in that point, okay? And so this is the Sinatra pipeline, and I'm going to roughly talk you through parts of it, okay? So for statisticians, a very classic way of thinking about this problem is what's called a Bayesian hierarchical model, okay? So just like before, my functions f, my regression functions, are a Gaussian process, okay? Now, I take these functions and I tell you that my y is, well, it's 0 or 1, right? And so I'm going to say that y I draw from a Bernoulli random variable pi. And that pi, right, is related to our function f as follows. Pi over 1 minus pi, the log of that is equal to f. This is called a logit function. This is kind of some really standard statistics of how you can model binary variables, okay? Now, what you get out of this is a Gaussian process, or some people like to call it a kernel model. Now, in other work we've done, we figured out a way of how to get the analog of what's called an effect size. So for all the people out there who've done regression, right, just linear regression, right, what is that? Y is equal to beta transpose x, right? And the classic formula for estimating beta is x transpose inverse x transpose y. Okay? It's just a linear projection operation. Okay? So you can extend that to nonlinear functions as long as they're smooth and high dimensional. And there's some kind of cute Fourier analysis that lets you do this efficiently. Okay? But what that basically does is it lets you go back and say, for each direction, for each distance in t, right? How much did that contribute to the regression? That's what these betas are. These are what we call effect size analogs. Okay? So now I have these, but I want to know how important they are. Okay? So now one of the things that was nice here is we used a Bayesian method, so that let us simulate these betas many, many, many times. So I have a collection of these vectors of betas. So now what I can do is I can take, if I'm interested in, let's say, the jth beta, let me take it out. By that I mean I set it to 0. Okay? And I will approximate that multivariate distribution with that j set to 0 or removed, actually removed as a normal. I can think of that as a normal distribution. And then what I can do is I can look at the conditional probability if I remove that jth beta, conditioned on what the jth beta is. Okay? And again, I can approximate that normal, and I can closed form compute this KL divergence. So this KL divergence is telling me if I were to remove this beta versus keep it in, right, how much extra information do I have, right? How close are these two distributions? And then I just normalize everything so it's between 0 and 1. Okay? This is a measure of the marginal distance. And so if gamma j is much bigger than 1 over p, you get something that's interesting. So now that we've found interesting betas, how do we pull them back? Right? This is what I said. I found the largest gamma ij's. I can think of that as a direction and a distance. How do I pull it back? So you can try to do something like this formula. So if you knew how these heights align, right, in a small cone, I can basically use projective geometry to pull it back. Okay? We actually don't exactly do this in our paper. On our paper, we use a intersection argument because it's more robust. But if anyone wants to know about that, please talk to me. I'm happy to tell you more. Okay. So I wanted to show you some results. First, 1 second. So this is a null. I'm going to show you 2 null models, okay? So we actually, one of the things that we really were happy about in our paper, and we worked hard on, is how to do reasonable simulations, okay? And we have 2 kinds. One are these spheres. The other one is we have caricatured teeth. And so if you're interested, you can read in our paper how we did that. But so here we have one shape. And I'm sorry. Basically, we generate a bunch of random shapes that all look like this. So they're all in the same family, right? So that's one type of null. And the point is that if I look at the false color, with red being very high and these being less so, you don't get anything that's really, really different, right? So under that null model, you don't find any interesting points. Now, if you have very smooth shapes as class 1 and these really crazy shapes as class 2, again, you're not going to find anything significant because everything's different. So all those gamma j's are about the same value, okay? So that's one version of a null model. Now, where did I go? Okay. So we also thought about some real data, and let me just make this a little bit bigger. Okay, so this is, I'll go back and forth, okay? So we know that in the tarsus, which are a type of lemur, there is this periconid. And we know that like that's slowly lost as you go evolutionarily further away, right? So what we're showing is some notion of evolutionary distance, right? I'm showing the most common ancestor. Okay. And so what we did was we compared the tarsus to the samiri, the tarsus to the mirza, and the tarsus to the microcebus. And these are all, by the way, monkeys. And we asked the question, how similar or different do they get? And you can see as we get evolutionarily further away, you get more significant points. You see more differences in the teeth, right? So that was kind of interesting. Okay, so the last part of this talk is I'll spend just a few minutes talking about how you can actually build proper evolutionary models and a Gaussian process notion of fiber bundles. Okay. So I told you there's this notion of a Gaussian process. And again, I'm thinking back to that fiber bundle picture where the evolutionary process is living on a manifold, and it has some type of covariant structure given by this evolutionary kernel. And then conditioned on the evolutionary process, we have a fiber bundle process. And again, that has this covariant structure given by fiber. Okay. There are certain classic evolutionary problem models. This is called an Ornstein-Uhlenbeck model, which is Brownian motion with drift. It induces the following kernel. There are other types of kernels called early burst models. This is just stating fiber bundles. The key point, the key point is the fiber bundle introduces a local trivialization. So I have a product structure between the base manifold and the fiber. That's a really, really important point. Okay, and so let me actually skip ahead. Well, I'll come back to it, sorry. Okay. So one idea people have are something called structural correspondence maps. So this is one tooth and another tooth. You can try to define a map between them by basically minimizing some type of variational problem between these two. It could be optimal transport, which is actually what's being done here. So you try to minimize this using some type of diffeomorphism. Okay. So this is just what's called a correspondence map. Now, typically people have thought of these maps as deterministic, and we're going to make them probabilistic, but we'll talk about that in a second. So I told you this is Gaussian process before, but now I'm going to define a Gaussian process, and I'm going to index it on a fiber bundle. Okay. Now, what's nice is because of the trivialization property, I can think of the Gaussian process on this fiber bundle as having a base manifold part, which is the evolutionary part, product with the fiber part, and that comes with the trivialization. So the fiber part is just based upon that structural correspondence map, okay, just scaled. What I wrote here, and I told you already what the evolutionary models are. So now we can actually do model selection. If I give you two evolutionary models, I can actually marginalize out the what's it called, the fiber part, and give you evidence in terms of these types of ratio tests. We actually have some results, which I'm not going to show you, but if people are interested, please send me an email on comparing. We have a collection of lemur molars from Madagascar, and early on, people very much thought they fit something called an early burst model, which means initially, as whatever the ancestors were got to Madagascar, they very quickly evolved away from each other, then things slowed down. And what we can formally show using this idea is that there is no greater evidence for the early burst model than there is for Brownian motion. So we don't have strong evidence for it. That Gaussian process, it's related to when you have these covariant structures, so these Gaussian processes, there's actually a covariance kernel there, and that has, in the classic sense, an infinitesimal generator. And again, this Gaussian process on fiber bundles has an infinitesimal generator, and that is what Tingran Gao worked on for his PhD thesis, with something called rough horizontal Laplacian. There are works to move beyond parallel transport in this setting. This is work with Tingran, Jacek, and myself. And now we're looking at, there's a very pretty Ito calculus on Riemannian manifolds that comes from the theory of Eels, Ellsworthy, Malevin, and also Struck worked on this. But they always assume there's Brownian, they also assume there's parallel transport. Now, because we're working with real data, what we know is that when you go from one shape to another shape, you actually have errors in coordinates. So there's this very interesting thing is, how do I introduce that into this Ito calculus? And so what's going to happen is, in a way, as shapes go further and further from each other, you have a lack of integrability, right? You you start introducing more and more errors, you start introducing torsion, right? And so how you actually think about these Lie brackets that have this torsion is quite interesting. There are lots of other really interesting open questions, and there are people who gave money and we talked to, and I'll stop.
Well, if you're in the audience, please unmute yourselves, and let's give a round of applause to Cheyenne. So, questions for the speaker?
You can also send me emails.
I have a question to start. This
Yeah.
early burst model, which you're finding evidence against, or at least no evidence for. Do you have any hypotheses why people got confused by this at first, or is this something that you got? Yeah, go ahead.
So I think that I guess this will probably show you some of my biases. But, I think we as people want to believe things are really like, that everything is happening for a reason, right? And it's not random, right? So people want to believe that everything that changes is changing because the environment's changing or there's a selective pressure, right? And we don't always like to test against the null model that it's really just random, right? Classic version of this, if you just take classic version of this in genetics is coalescent theory, right? If I look at Galton-Watson trees, if I just take people's last names, right, and I ask the question of why did someone's last name go 10 generations whereas someone else's only went 2, right? And you can say, well, it happened because there was pressure, or this last name was better at, hiding from snakes, right? I really mean genes here, but you don't. But it could be just random. It could really have just been random because one of them's going to last longer, right? So making this more formal is important, and I think one of the highlights that we've seen a lot in classical in classical phylogenetics is that it's sometimes really hard to show greater evidence than there just isn't, it's not selected on, right? So yeah.
Other questions? Oh, you're muted, Tomas. Oh, no, that was a wave goodbye. Final questions? Well, thanks so much, Shine. We greatly appreciate it. And we'll be meeting next, I think, in 3 weeks' time.